We are going to skip section 3.2 because the discussions therein are subsumed by the discussion in section 3.3. In this section, we are going to make rigorous the analogy between information theory and set theory by the construction of a signed measure called the I measure, denoted by mu star. Let x tilde be a set corresponding to a random variable x. Fix n and let n sub n be the set of integers 1, 2 up to n. Now we define the universal set omega to be the union of all I xi tilde. Then the atom A0 defined as the intersection of all I xi tilde complement, which by De Morgan's law can be written as the union of all I xi tilde complement. Now we see that the union of all I xi tilde complement is simply equal to the universal set that we have defined, and so this can be written as omega complement, which by definition is equal to the empty set. For this reason, we call the atom A0 the empty atom of Fn. We let A be the set of all the other atoms of Fn, called the non-empty atoms of Fn. Note that the size of A is equal to 2 to the power n minus 1 because we exclude the empty atom. We have seen that a signed measure mu on Fn is completely specified by the values of mu on the atoms of Fn, but because of our special definition of the universal set, the atom A0 is always empty, and so mu A0 is always equal to 0. For this reason, a signed measure mu on Fn is completely specified by the values of mu on a set of all non-empty atoms of Fn, namely the set A. We now look at the simplest example with n equals 2. Here, omega is equal to x1 tilde union x2 tilde. The empty atom A0 is equal to x1 tilde complement intersect x2 tilde complement. This is shown in the Venn diagram at the bottom. Now, because A0 is always empty, we can simplify the Venn diagram to the information diagram shown on the right. For simplicity, the set variable x1 tilde is shown as x1 on the information diagram, so on and so forth. In this information diagram, the non-empty atoms are x1 tilde intersect x2 tilde, x1 tilde complement intersect x2 tilde, and x1 tilde intersect x2 tilde complement. These are indicated in the information diagram. Note that the size of A, namely the number of non-empty atoms, is equal to 2 to the power 2 minus 1, which is 3. Then, a signed measure mu on F2 is completely specified by the values of mu on the atoms of A, namely mu on x1 tilde intersect x2 tilde, mu on x1 tilde complement intersect x2 tilde, and mu on x1 tilde intersect x2 tilde complement. We now introduce some useful notations. For non-empty subset G of the index set n sub n, let x sub G be the collection of random variables xi, I in G, and x tilde sub G be the union of all xi tilde, I in G. Theorem 3.6 is a very important theorem. Let script B be the set of all xg tilde such that G is a non-empty subset of the index set n. then a signed measure mu on Fn is completely specified by mu b, b in script b, which can be any set of real numbers. Now this is the significance of theorem 3.6. We have previously seen that a signed measure mu on Fn is completely specified by a set of numbers mu a in script a, the set of values of mu on non-empty atoms. This theorem says that mu can instead be specified by mu b, b in script b, the set of values of mu on the unions. In Appendix 3a, we show that for any a in script a, the set of non-empty atoms of Fn, mu a can be expressed as a linear combination of the values of mu on the unions of xi tildes. First, it is easy to check that for a set additive function mu, mu a1 union a2 is equal to mu a1 plus mu a2 minus mu a1 intersect a2. Now, by rearranging the terms, we obtain mu a1 intersect a2 equals mu a1 plus mu a2 minus mu a1 union a2. Note that 2 can be obtained from 1 by exchanging the unions and the intersections. Here we replace the union by the intersection, and here we replace the intersection by the union. We also note that equation 1 is a special case where m is equal to 2 of the inclusion-exclusion formula, which says that mu of the union of ak from k equals 1 to m is equal to summation mu ai for all I minus the summation of mu ai intersect aj for all distinct pairs I and j, plus all the way to minus 1 to the power m plus 1 mu of a1 intersect a2 all the way to intersect am. Theorem 3.19 in the appendix is a variation of the inclusion-exclusion formula. The proof of this theorem is elementary. For the details, please see the textbook. To understand this variation of the inclusion-exclusion formula, we cover all the minus b in the formula and observe that this formula is just the inclusion-exclusion formula with all the unions replaced by intersections and all the intersections replaced by unions. We are now ready to prove the claim in Appendix 3a, that is, for any non-empty atom A of Fn, mu A can be expressed as a linear combination of the values of mu on the unions of xi tildes. First, for a non-empty atom A in A is equal to the intersection of yi for I equals 1 up to n, where yi is either xi tilde or xi tilde complement, and there exists at least one I such that yi is equal to xi tilde. Otherwise, A is equal to the empty atom. Then we can write A as the intersection of two intersections. The first intersection is the intersection of all xu tildes, where u is such that yu is equal to xu tilde. Basically, what we have done is that we group all the x tildes and put them in the front, and we group all the x tilde complements and put them at the back. For the second intersection, it is the intersection of all xv tildes complement for all v such that yv is equal to xv tilde complement. By applying De Morgan's law to the second intersection, we can write this as the union of xv tilde for all v, and then we take the complement. Equivalently, we can write this as minus the union of all xv tilde for all v. This form is exactly the same as the one on the left-hand side of theorem 3.19, where ak is equal to xu tilde for some u, and b is equal to the union of all v, xv tilde. By applying theorem 3.19, we can express mu a as a linear combination of terms of the forms on the right-hand side of the theorem. We now invoke an elementary identity in equation 2 that can easily be verified. It says that mu a minus b is equal to mu a union b minus mu b. Then apply 2 to each term on the right-hand side of equation 1. For example, mu ai union aj minus b is equal to mu ai union aj union b minus mu b. Since b is a union of xi tildes, the right-hand side above is a linear combination of the values of mu on the unions of xi tildes. Thus, we have expressed mu a of a non-empty atom A as a linear combination of the values of mu on the unions of xi tildes. We are now ready to prove theorem 3.6, which says that a signed measure mu on Fn is completely specified by mu b, b in b. That is, we can specify a signed measure mu on Fn by specifying the values of mu on the unions. The proof goes as follows. First, recall that the number of non-empty atoms in Fn is equal to 2 to the power n minus 1, and a signed measure mu on Fn is completely specified by mu a in A. That is, we specify the value of mu on the non-empty atoms, and this set of numbers can be any set of real numbers. The set B is indexed by all the non-empty subsets of the index set script n. So, the size of script B is equal to the size of script A, which is equal to 2 to the power n minus 1, and we call this quantity k. Now we let U be a column k vector of mu a in A, and we let H be a column k vector of mu b in B. Now for each b in B, mu b, which is the value of mu on a union, can obviously be expressed as a linear combination of mu a in A by set additivity. In fact, this linear combination is a summation. Therefore, we can write H is equal to Cn times U, where Cn is a unique k by k matrix. On the other hand, we have shown in Appendix 3a that for each A in A, mu A can be expressed as a linear combination of mu b in B. Therefore, we can write U is equal to d sub n times H, where d sub n is a k by k matrix. Combining equation 1 and equation 2, we have U is equal to d sub n times H, and H is equal to C sub n times U. So we can write this as dn times Cn times U, which is equal to dn times Cn together, and then times U. Then obviously, dn times Cn is equal to In, the K by K identity matrix, showing that Dn is in fact equal to the inverse of Cn. Moreover, since Cn is unique, Dn is also unique. Therefore, mu B, B in B, is related to mu A in A, through an invertible linear transformation. Hence, mu B, B in B completely specifies a signed measure mu on Fn.